Okay, first question. Prove that the moment of inertia of a uniform square mass of M and side D about an axis through its centre parallel to a side is a half md squared. Okay, so first of all what we're going to draw here is we've got to draw our square. Okay, so our square is this here. Okay. Now that we've drawn our square, we know it's of length D. Okay, so this side here is length D. Now that's done. What we gotta do next is we gotta figure out what's happening. Okay, so its axis is in the middle. It can be the middle any way you want. It's a square, so it doesn't really matter which way you go about drawing this. So I'm just gonna draw it this way. So that's the axis. Okay, so prove that the moment of inertia of a uniform square mass M and side D about an axis, so this is about the axis through its centre, an axis through its centre parallel to a side. It's parallel to this side here, so we can see that we've set up the appropriate system. Okay, next thing is we're going to, the formula that we're always starting off with in this chapter is DI. You can skip straight into this if you want. DI equals x squared dm. Right, it means the moment of inertia is x squared multiplied by the change in mass. Okay, so it's just an integral. Okay, so what we're going to do next with this integral is we're going to set up we're trying to find out what it is for any part of the mass. So here I'm taking a really thin strip. Okay, this is a really thin strip here. Okay, any sample of any part of the square. Okay, now this is a distance x from the center. Okay, its width, the width of this is dx. Okay, now we've got to remember dx is so tiny that's considered still to be a distance x away. Next thing is, what is the mass of this piece of area? The mass is dm. Okay, now next thing we're going to find is rho. Rho is going to be the mass per unit area. Okay, because we're talking about an area. So to get this, what we need to do is we need to get the full mass of the object is m, and the full area of the object is d multiplied by d, which is d squared. This means that rho equals m over d squared. Okay, it also means that m equals rho d squared. Okay, oh sorry, yeah, that's grand. Now next thing is we're going to figure out what to do with dm. dm, which is the size of this piece of area here, it's equal to rho, which is the mass per unit length, or sorry, mass per square unit, multiplied by the area. So your mass per unit area multiplied by your area gives you the total mass of that section there. Okay, so that's what it means in English. Okay, this is the mass of the area, this is the mass per unit area, and this is the area of that part there. Okay, so makes sense. The next part after that is, we now got to change it. The variable is x, so we now have to try and find a way to change the area into a variable of x. Okay, so what is the area of this little square here, or this little rectangle? Okay, so if I was to draw this out, okay, what it is it's d wide and it's dx long. So the area is d dx. Okay, d multiplied by dx. Right. So what we're going to do is just going to get rid of that now. So that is now rho d dx is dm. Rho d dx. Okay. Now what we can do next is we can change rho into m over d squared. M over d squared d dx is dm, and then eventually what we're going to have is dm equals m over d dx. Okay, so m over d dx. Now go back to your initial formula, this one here. So what we'll do is we'll let us copy and paste that down. Okay. Okay, x squared dm. I'll do this part in blue. Okay. So what we have here is we're going to change dm. So now we're going to have di equals m over d dx. Okay, so m over d dx. Now integrate both sides. When you integrate di, you get I. We're going to integrate this side. Now this here is a constant, isn't it? M is fixed because it's the mass of the entire system. D is fixed because it's the length of the entire system. Okay. So we're just going to get our x squared dx there. So I've got the x squared part. I replace dm with m over d dx, and there's still x squared in there. Okay, so I'll just rewrite that. Actually, it's a bit messy. So integral sign of x squared dx. Okay. Now, what are our limits for this question? If this is the center part, it goes a distance d over 2 above, and it goes a distance d over 2 below. So that means it's going to be d over 2 and minus d over 2. Okay, so that's where those two limits come from. The next part is just very much just about integrating them. Okay, so what we're going to do is when we integrate them, okay, so what we're going to get here is I equals m over d on the outside, and it's going to be a third x cubed from d over 2 to minus d over 2. And then when you integrate this, it's going to be m over d brackets a third d over 2 cubed. Okay, I'm just going to put it in a larger set of brackets here, the red brackets separating out the m over d. Okay, and then the second part is going to be minus a third, put this in green, that's the second limit is going to be in green, a third minus d over 2 cubed. What in effect that's doing is because it's a cubed, the whole thing is going to be minus a third d cubed over 8. It's going to be minus 1 over 24 d cubed, or minus d cubed over 24. Both of them are minus d cubed over 24. So it's going to be d cubed over 24 plus d cubed over 24. Yeah. That's going to be 2d cubed over 24, which is the same thing as d cubed over 12. That's d cubed over 12. Put it back inside. The d's will cancel. That d will cancel with that d. And what I'm going to be left with is I equals md squared over 12. Asked, okay? So okay, so that's it there, okay? Trick is with this question is just just to make sure you know the routine. Routine is everything, okay? They're very similar. The next question is the radius of gyration, okay? And the radius of gyration is how far it would be away from the axis if it was treated all as one mass, okay? It's very much doesn't matter. The radius of gyration is very much doesn't matter if you're using the formula every time. I equals mk squared. K is the radius of gyration. So all we ever have to do with the radius of gyration is plug in your answer from the last section, which is md squared over 12. That equals mk squared. The m's will cancel, and then you'll get k equals d over root 12. Oh sorry, just give me a second. No, I'm looking at the wrong question. Oh yeah, I'm good now, okay. So equals the square root, k equals the square root of d squared over 12. And when you put that in, you're going to get d. Put root 12 into your calculator and you get d root 3. And that's part 2 for the radius of gyration. Okay? So that's it. Very, very easy to do a radius of gyration. Okay? Again, this one here. A uniform analyst consists of a disc of radius 3 meters with a disc of radius 1 meters removed from its center. The mass of the analyst is m. Prove that the moment of inertia of the analyst through the center perpendicular to its plane. Through the center perpendicular to its plane would be that rotating around this way, like a, I suppose, how will I draw this? Basically like you get that there. CD around a thread almost, okay? So that's what you're looking at there. Now that's done. The mass of analyst prove that the moment of inertia of the analyst without an axis through its center perpendicular plane is 5m. Okay, that's fair enough. Alright, start off like we always do. We're gonna do what we did last time. We're gonna try and get a small slither of the disc, okay? So I'm gonna put it right to the edge now, and then just put this in here. Now see the black ring? The black ring is the DM, if you will. Okay? It's now in red. So that's the little slither. We're gonna find out what its dimensions are and how it works, okay? So we're going to start off, like as I said, I'm going to write down this formula, okay? Now, it can be x squared dm, it can be r squared dm. The main thing is, it's some unit of length dm, okay? It can be either, okay? Next thing is, we're going to define rho. Rho is like last time, it's mass over area. This is area. This is for the full disc, okay? So the mass is going to be m, and the area of the disc. Anybody? Now the area of the disc is more difficult because it's a big disc. Take away a small disc, so it's going to be 2 pi times 3 squared minus 2 pi times 1 squared. Big one minus the small one. Okay, that will turn into m over. Oh, sorry. Excuse me. It's not 2 pi. It's pi r squared. Excuse me, because I know it should be 8 pi squared, so it's not, it's pi r squared minus pi r squared. That's going to give you 8 pi, so m over 8 pi is our rho. Okay, now that we have this done, sorry, that's everything up there, that's it. Right, never mind. Okay, next part is, let's work with this, right? R squared dm, they're sort of incompatible, okay? So let's define r as the distance, whatever this variable is here. See the way I have r squared dm? It's always defined as the distance to this little area you're talking about. So in this question, I'd call it r. There's no reason why I can't call it x and get the exact same answer, because you're going to be integrating anyway. Now, once you call that one r, you also have to obey the same rule. So when I chop this in half, so I'm going to chop this in half, and it forms a rectangle. Okay, and when it forms this rectangle, what's going to happen is it's a really thin rectangle. Okay, and this thin rectangle, if I call the distance away from the center r, that means I'm obliged to call the width dr. Okay, now what's the length of this? Can anyone tell me? 2 pi r, because it's the circumference of a circle, isn't it? Now, once again, why is this side the same length as this side?
Because it's negligible that it wouldn't matter.
Yeah, they are different, but the strip is considered to be so thin that the difference in length doesn't matter. So small, doesn't matter. Okay? That's what integration is, taking such small pieces one by one that it doesn't matter. Okay? Next thing we're going to do is we're going to try and sort out our dm here, okay? So dm is rho dA, like last time. We're going to then change dA into area. And what is the area of that little thing? It's going to be 2 pi r dr. So rho times 2 pi r dr. Once you've done that, we still haven't got it, but yeah, we actually have it pretty workable at the moment. We're going to change rho into m over 8 pi. You can do that later on if you want, but might as well do it now. It'll get rid of the pi for you. Pi goes, 2 over 8, 1/4, so m over 4 r dr. Okay. Okay, just try to neatly put that in there so everybody can see it. Okay, next one is we're now at this point here, so we're going to change this to di. The dm changes into m over 4 r times r squared dr. Okay, and if we integrate both sides, okay, now di integrates to I, and this is going to be, we can integrate the m and the 4 inside it if we want. Like, we can take it outside or we can put it inside. What way do you guys prefer?
Take it outside.
Take it outside, okay, that's not bother. We can do that. So dm over 4 is a constant, and inside we're going to be left with r cubed dr. Now, the difference between a radius question from the proof we did the last day, so the difference between a circular question and the laminar question is the way you present the limits. Okay? Now, you might go up and go, well, is it not r to minus r? It would be for a full circle. Oh, sorry, it wouldn't be. If it was a full circle, it's just 0 to whatever your radius is, like the proof. Okay? 0 to whatever the radius is. But in this question, because it doesn't go right back to 0, does it? It starts off at radius 1 and it ends at radius 3. This makes the limits 3 and 1. Okay, 3 and 1. Okay, next we integrate. I equals m over 4. Okay, and then we're going to get 1/4 r to power 4, 3 and 1. Okay, put this in red brackets there to separate it out. Next thing I'm going to do is I equals m over 4. Close bracket here. We're going to get I'm trying to think, 1/4 of 81. 1/4 of 81. Sorry?
20.25.
is a quarter of 81.
Yeah.
Oh, yeah, it's not necessary. Yeah, I'll show you why. The next one's just going to be minus a quarter. So it should be yeah, it's going to be 20 over 4. So it's going to be, if I move the quarter outside, it's going to be m over 4 multiplied by, what's it going to be, 80 over 4, and that's basically 80 over 16, which is 5m, which is what we're asked to prove. Okay, so you can see it's actually quite repetitive. The only thing you got to remember is you treat the limits differently for the circle than you do for the lamina. It's actually a repetition of itself. Okay, so a uniform lamina, a rectangle lamina of length 2L and width 2K. So let's set out our 2L and our 2K. 2L, 2K. Okay, now that that's done, you want to show, prove that the moment of inertia about an axis along the side K. An axis along the side K is 4ml squared. Okay, I have a choice of the axis this time. Okay, so the axis can be it can be here, or it can be here. Sorry, that's actually meant to be on the line. So I have a choice. I'm going to choose the left one because it means that my limits will be positive. If I choose the right one, my limits will be negative, but it should still come out as the same thing. Okay, so this is my axis. Okay, now that that's occurred, what I'm going to do is I'm going to do what I always do: set up a small area at a certain distance away from the axis. Okay, now this here is we're going to call it dA. Now remember to write down the one formula you had learned off by heart. dI equals x squared dm. Since we're using x this time, no reason why, just decide x is my letter. The distance of this area from the axis is x. The width of this little area I'm talking about is dx. Now I'm going to go through my routine. My routine is, I have to figure out what rho is. Rho is mass over area. And mass over area is going to be m over, what's the area of that? 2L, 2K, which is, now does it say anything about the mass? Oh, it's 3m. So the mass is 3m this time. So it's going to be 3m over 4KL. Is that alright for starting off? Okay. Next thing we gotta do is I gotta set up a big integral with x as the variable. Currently dm is preventing that, so I need to sort out dm. So at the moment my integral is blocked by the presence of dm. I need to change dm to dx. That's always the next step. So the dm is rho dA, because it's the mass per square meter by the actual area, mass per square area by the area. Next thing we're going to do is going to change dA, so it's going to be rho times, what's the area then?
dx
2k multiplied by dx. To my knowledge. Yeah, 2k dx. Because, anybody know what's 2k dx? The width of this is 2k, and technically you always say the shorter one is the width, so the width is dx and the length is dk. Same thing, right? So what we're going to get is 2k dx. Yeah, looking at that. 2k dx, okay? Now we're going to introduce rho into the equation, so we're going to get 3m over 4kl. 3m over 4kl, 2k dx. Let's get rid of those k's. Let's get rid of that 2 and turn that into 2 there. So we're going to get is dm equals 3m dx over 2l. Okay. Okay, so that's over there. A nice neat little package, okay? That's the DM sorted, right? So that little part there is the DM. Alright, next thing I gotta do is I'm gonna sort out where I originally started, okay, with the di equals x squared dm. Di now equals I suppose it equals x squared times 3m dx all over 2l. Do we have any constants there?
3m over 2l.
3m over 2l is my constant, and this is my x squared dx over this side. Okay, next thing I gotta do is integrate both sides, because I'm only talking about a small bit of inertia. I'm not talking about the total inertia. To change a small piece of inertia into the inertia of the entire body, we integrate. That's what that means, right? So integrate both sides. Sorry, my integration sign should be over here. Now, what's my limits? 0 to 2l, all the way across, okay? So, what we're going to get is, when you integrate the I, you get I. When you integrate this, it's 3m over 2l. The integral of, what did I say again, 2l to 0. And then what we're going to get is x cubed over 3 from 2l to 0. Integrate. I equals 3m over 2l. Multiply by 2l to be cubed, anybody? 8l cubed over 3. Let's cross off some stuff. 3, l with that l, 8 with that becomes 4. I'm just looking at 4l squared, haven't I? Is that what I missed?
Yeah.
Oh, sorry, 4ml squared. I equals 4ml squared. Okay.
Can you go back to how you got the limits again?
Yeah, just give me a sec. The limits were gotten by going back up to the axis. This is my axis, and this full body, the whole body, goes a distance 2l away. So at the axis itself, there's no length until you start coming out, and then it goes all the way out to a maximum length of 2l. So that's why the top limit's 2l and the bottom limit is 0.
So it would be down the would be x minus x.
If I had to put an axis, if I got a question where I had to have, sorry, I'll do this right. If I had a question where it was demanded that my axis of symmetry, my axis of rotation, or was a distance, let's say the entire system's 4l, and that there's still 2k, and let's say I was told that's l away. So it would be minus l to the left and 3l to the right, so it would be 3l to minus l. It depends on where my axis is. Is that right? Radius of gyration, okay, once again, it's just a matter of looking up that formula. Radius of gyration is I equals mk squared. Replace I with 4ml squared equals mk squared. M's will cancel. K squared equals 4l squared. Square root both sides. K equals 2l.
Yeah.
Oh wait, no, the mass isn't. It's 3m. There we go. That's where I went wrong. So 3mk, so that's 4 over 3, and then it's going to be 2 over root 2l over root 3. That's just keep an eye on those m's. That's one mistake I make a lot. I forget to check the mass. I just put down as m. I don't keep checking back to see if it's m or 3m or 5m.
So that's to show that it's 2l.
No, the answer is 2l over root 3. What's the question say?
Show that the radius of gyration is 2L.
Over root 3. Okay. Does it say 2L in your book?
Yeah.
So it's obviously a mistake there, okay? In the question. So it's meant to be 2L over root 3. Okay, because his solutions are contradicting his... He actually made the same mistake I did. He forgot to put in the 3M. So it shows you if he can do it. Okay. So, you happy enough for next question, yeah? Next question. Okay guys, prove that the moment of inertia of a uniform analyst of internal diameter y and external diameter 7y and mass am about an axis through its centre perpendicular to the plane is 50 my squared. Now, exactly the same question we had last time. It's one of these ones with that's the disc. The centre is y, so I'm going to make that centre a lot smaller maybe. Yeah, y and 7y is a lot, that's out of proportion there. Going to make it really small in the middle. Okay, so that's a bit better, alright? Now, this here, radius y.
It's diameter y.
So yeah, diameter y. Even worse, y over 2. Okay, y over 2. The external radius, 3y over 2. The axis going as external body about an axis through its centre perpendicular to the plane. Perpendicular to...
7y over 2.
Yes, it is. 7y over 2. And I would miss the centre. Okay, I have an idea. This is... Ooh. Okay, so what we're getting next is 7y over 2. Okay, so okie dokie. Let's start the way we always start. We're going to write down the I. Now, it's a radius one, so let's write down r squared dm as opposed to x squared dm. Once again, makes no difference. Okay, now that we have that done, what we're going to do next is we're going to go through what we always start off with. I always start off with rho. Rho is defined as mass per unit area, yeah? So it's mass over total area of the object. Now what's the mass? am this time. Be careful about that. Now the area is a tricky one. It's going to be pi times 7y over 2 squared minus pi times y over 2 squared. The differences in the two areas of both circles. Okay, then what we're going to get here is 8m over, what's that going to be, 49 pi over 4 y squared minus pi y squared over 4. That makes 48 on the bottom. 48 over 4 technically speaking.
Well.
Yeah, it's going to be 12, isn't it? Yeah, I'm happy with 12. So we're going to have 12 pi y squared over 8m. And then when we finish that off, it's going to be 2 over 3. Then tons of variables there. It's going to be m pi y squared. Okay. Now, we'll do next. Just resize that. Okay, that's that part done. The next part we're going to have to do is we're still working off the I equals r squared dm. Now we need to sort out what dm is. So what we always do. We're taking, if I can just rub this out for a second, okay. What we're taking is a little slither of the system, okay. So no, that doesn't work. Okay, so if you can imagine It ain't gonna work either. Alright, I'm gonna try 2D because it's easier. Alright, here's a two-dimensional representation of what I just did there, right? So you have the center cut out. Okay, and that's the center cut out. Now what I need to do, and I'll do it as a red circle here, is I'm gonna just show you where my not a filled in circle now. Don't know why it's doing that. Ah, that makes sense. Okay, let's try this again. There we go. Right. So we're gonna. I got it. So there's two circles on the outside, okay, and then the circle on the inside, which is which was meant to be black, okay, is still there in the center. Now, one of the worst diagrams I've ever done, but we'll work with it. Alright, this here is our perfectly symmetrical center, our circle, and this is the distance we're working with, okay? Now, its distance away is dr. The width of it is, the distance away is r. What is the width of it? Dr. Okay, so the width of it is dr. When we split this up into a rectangle, which we can do, it's basically going to be 2 pi r in length and dr in width, exactly like last time. Now we're going to start off with dm. dm equals rho dA. dA equals 2 pi r dr. Change rho into, what did we say rho was? It's over there, isn't it? 2m over 3 pi y squared. 3 pi y squared, 2 pi r dr. Right, now that's a mouthful. Okay, so we're gonna have to start crossing stuff off. Let's cross off let's cross off these ones here, okay? Now what we're left with next is we're going to have dm equals what's it going to be, 4 over 3 y squared r dr. Now let's get our formula.
4m. Yeah, 4m.
M on top, thank you. di equals r squared dm. Now integrate both sides and change that to a dr. So because rho times, excuse me, so it's going to be 4m over 3y squared, r squared plus r cubed, not plus, multiply. Now limit time. Okay, what is our limits for this question? Now remember, we're integrating the entire system. It starts here technically because there's nothing in here. So it starts at y over 2 and ends at 7y over 2. So 7y over 2, y over 2, and we're going to integrate now. Okay, so we're going to get I equals 4m over 3y squared. Integrate, and when we integrate, a quarter r to the power 4 from the limit 7y over 2 y over 2. Now that's quite difficult, okay? Algebra wise it's quite taxing, so what we can do here is we're quartering absolutely everything, aren't we? Quarter is technically a constant, isn't it? So let's scratch it off with that one. That will make that easier. And now what we can do is we take that 4 off, So we can say 7y over 2 to the power of 4 minus y over 2 to the power of 4. Don't bother with, go straight to the calculator, ignore the y's, and just do 7 over 2 to the power of 4. Minus, what's that going to be? Minus a half to the power of 4. Okay, minus a half to the power of 4, okay? So I just like using my...
150.
I'll see you in a second, sure. $150, well done, okay? This was obviously a lot faster than I am with my computerized calculator. So, what's that? 150 y to the power of 4 multiplied by m over 3y squared. Then we're going to get, what's it, 50my squared, is it? And that's what we're asked, wasn't it? Okay, guys.